Now we're going to be thinking about a topic called reaction diffusion. So this is about the way that when certain inputs combine to produce an output, it occurs in a spatial context so that that output then can spread out or diffuse from its place of origin to other areas and affect what's happening elsewhere. So this might be a way, for example, of thinking about innovation in cities, because a city is a place that concentrates a lot of people, and so it tends to be a hotbed of innovation or the generation of ideas. And those ideas that are then generated in the city spread out into the surrounding landscape and reach maybe other cities, then perhaps combine with ideas that are already there to generate new ideas that then spread out or diffuse in turn. And this may help us think about why human settlement patterns consist of cities, towns, and villages, a hierarchy of concentrated settlements rather than just a uniform spread of settlement across the landscape, just a uniform distribution of scattered houses. So to think about this, we firstly need to think about diffusion. So diffusion, occurs when this is a beaker of water. You drop a particle of ink into the water and it gradually dissipates and spreads throughout the beaker. And so the drop of ink will eventually fill the whole beaker, and instead of having a drop of ink in clear water, you'll have murky, inky water. So we define, first of all, the density of, in this thinking about this, the density of the ink in the water, U. And this is a function both of position and time. So at the start, the concentration of ink is very high where the ink's just been dropped in, whereas in the corners of the beaker, there's no ink reached it yet, so they're still clear. So the concentration is 0 or low. So that's saying that U depends on X, the position. But over time, as the ink spreads out, then the concentration increases in all the other areas and decreases where it was first dropped in. So U is a function of both position and time. And then we assume that if we've got a high concentration here and a low concentration here, firstly the substance is going to flow from high concentration to low concentration, and the rate of flow will be presumed to be proportional to the steepness of the change in concentration. So here it's shown fairly steep, but if we had a shallow change in the concentration over that same distance, then the rate of diffusion would be less. There'd be less sort of force behind it, causing the particles to want to diffuse. Whereas here, where there's a strong concentration on one side and clear water on the other, it will be flowing more quickly across that line. So, in other words, what we say is that the rate of change of the concentration, or at least let's just say the flow through the point, is proportional to how much the concentration is changing with X. So if it changes a lot in a small x, the flow will be greater than if it changes a small amount in a given x. So the flow is proportional to du by dx, and we're using a partial derivative because it depends on both x and t. And to make it now a constant, sorry, to make it an exact sort of formula, we say the flow is equal to a constant d times du by dx. So it's a constant d times the gradient. And this d is the diffusion constant. And so if we're thinking about the change in concentration in a particular region, so we'll just work in one dimension at the moment. Here we've just got one x. So I mean, here it was diffusing in 2 or 3 dimensions there in a beaker of water. We'll just imagine something diffusing in one direction. So we'll have we'll say that this is the position x, and this is then x plus dx, and so the width there is dx. And here we've got a concentration gradient, we will say, of du by dx. And here we've got a concentration gradient of du by dx plus the change in du by dx for now, that. So going from x to x plus dx, the gradient will go from du by dx plus the change d in du by dx. And we can write that as the rate of change of the concentration gradient, d by dx of du by dx, times dx, because the dx's cancel out. So it's the rate at which the concentration gradient is changing multiplied by the distance over which the change has occurred, dx, to give the net change. And then this d by dx of du by dx we can just write as is just a second derivative. So it becomes plus d2u by dx squared times dx. And then, based on what we said here, the flow, and it's going to be in that direction if u is increasing in this positive x direction, then the flow is in the opposite direction. So coming out here will be d times du by dx, which is just that, and coming in here will be d into this du by dx plus d2u by dx squared times dx. And the net flow then will just be the difference between these. So it's flowing in is this and flowing out is that. So you can see that this flowing out d times du by dx is counteracting this flowing in of d times du by dx, and the net flow is d times d2u by dx squared dx. So it's dx. So that's a difference of that in minus that out. These are, oh, and forgotten the diffusion constant, which should also be in front. So plus d times d2u by dx squared times dx. Now that's the amount flowing in, but we're interested in the change in the concentration, which is the amount per, if it were a beaker, per unit volume, but here per unit length. So to get the change in the concentration, it is we're going to divide by the length of this, which is dx. So we've got d2u by dx squared. This is the, so we've divided by dx. That's the amount. This is the change in the concentration. Now this is the rate of change, remember, so we're saying that the flow is this. So this is per unit time. So this d times d2u by dx squared is the change in concentration per unit time. So that is the rate of change of concentration with respect to time. So this is the diffusion formula, diffusion differential equation. And we can then have this same thing in 2 dimensions, and it looks like d into d2u by dx squared plus d2u by dy squared, if x and y are the dimensions. And that's in 2D, and in 3D it would be d into d2u by dx squared plus d2u by dy squared plus d2u by dz squared. And to summarize that, this thing is known as the Laplace operator, which well, people write it, some people write it with a right way up triangle. I was taught to use an upside down triangle. It's called, or I would pronounce it, grad squared. So grad squared is, in 1 dimension, d2 by dx squared, and in 3 dimensions it is that, and 2 dimensions obviously just x and y. So that is another way of writing the diffusion equation using this operator, which, as I say, I would pronounce grad squared, and that is the diffusion equation. But now we're going to be talking about reaction diffusion. So let's have a look at that. So what can happen then if we think about chemicals for the moment and think in 1 dimension, is that we have a chemical that's a catalyst, say, for a particular chemical reaction, that's got a high concentration at a particular point. So it is catalyzing some kind of reaction here and producing some other chemical that then diffuses out to the surrounding regions. So that chemical is diffused to here and is sparking off some other kind of chemical reaction that then produces some new catalyst that diffuses back here and changes what's happening here. And so we can then, and that then, you know, changes the reaction happening here which then diffuses back to here and changes what's happening there. And so you can get kind of waves of concentration of different chemicals moving through space, and sometimes forming steady patterns. And in 2 dimensions, it looks something like this, where you've got patches of chemical reactions occurring in particular places and diffusing out and affecting what's happening in their surroundings. So you know, what's happening here is something different, as this catalyst that's being produced here diffuses out, and but it hasn't reached here yet, so this is the same reaction occurring over there. And the computer scientist Alan Turing suggested that this is a possible explanation for how something like a leopard gets spots. It's to do with the diffusion of chemicals, you know, when it's developing the embryo. The diffusion of chemicals in the pelt causes this kind of patchy pattern through a reaction diffusion process, and then that's sort of frozen in place and leaves you with these spots. And then in socio-historical systems, we can think of technologies as both the products of reactions between earlier technologies, insofar as technological innovation is a combinatorial process that's taking in old technologies and combining them to produce new technologies. So the technologies kind of catalyze reactions and to produce new technologies, and those technologies then diffuse from their place of origin elsewhere and then catalyze other innovation elsewhere. So, you know, it's a similar sort of situation, and may explain why we have technological innovation occurring in a kind of patchy way. If we want to represent that, or write an equation down then for the reaction diffusion, we're again let's just think in terms of chemicals as a sort of concrete mental picture. If we've got a set of chemicals which we chemicals from 1 to n, so we consider the concentration of the ith chemical ui, so we're interested in the rate of change of the concentration of the ith chemical du by di. Well, it's going to be a function of all the chemicals u1, u2 up to un. That's just describing how the chemicals react to produce this ith chemical, or, you know, which will depend on the concentrations of the other chemicals, how quickly they combine or react to produce this chemical. And then we'll add in a diffusion term, because it's produced, we've got the partial derivative, because this varies in space as well as with time. So it's being produced at a particular point depending on the concentrations of these other chemicals at that point, and then it's going to diffuse from there with our diffusion term, so grad squared ui, and then the diffusion constant di, because it will, you know, depend on how fast that particular chemical diffuses, because they may diffuse at different rates. So that's the equation for a reaction diffusion system. We're going to have some function describing how the inputs react, and then a diffusion term. And you know, we can apply this potentially to social systems. So in what's happening in a city may depend on the concentration of other things, like you know, the population, the existing technology, the available resources, things like that will affect the development of new technology, let's say, and will affect the change in the population. And then there will also be this diffusion term. So in the city, technology is being produced and diffused. In the city, depending on the existing population and technology available in the city, there will be people being born, and they may then diffuse out from the city. So the city is kind of and cities have been called social reactors. So it's a place where a reaction is taking place between various inputs, and it happens in space. So we can apply this kind of reaction diffusion model. So let's just have a look finally at just make that a little bit more concrete. We'll use the example of the Lotka-Volterra equations. So let's just write down the standard Lotka-Volterra equations to begin with. Okay, so that's the standard Lotka-Volterra predator-prey equations. Here x is the prey, so the rate of increase of the prey is reduced by the number of predators, y. So it tends to increase exponentially with ax, but it's then reduced by the predators according to this term minus by. And similarly for the predators, their rate of increase, the growth of their population, is proportional to the population, and it's increased by the prey. The more prey there are for them to eat, the faster their population will increase. But it has a natural tendency to decrease in the absence of the prey. So that's the standard Lotka-Volterra equations that we considered in the calculus part of the course. And now what we're going to do is say that this occurs in space. So rabbits and foxes actually live in space on the surface of the earth. So we, instead of talking about just the numbers of rabbits, it's how many rabbits are there here versus how many rabbits are there. It's the concentration of rabbits. So the higher the concentration in a particular place, the faster rabbits will be being born in that place. But also the higher the concentration of foxes in that place, the faster those rabbits will be being eaten. So we need to consider not just the numbers of foxes and rabbits, but if we want to understand it fully, we think about the spatial dimension. We need to understand how many rabbits and foxes are there in particular places. So that will create a pattern across the landscape. So we'll think of these x and y not as numbers of rabbits and foxes or predators and prey, but as the concentration of, in this case, the prey, and y is the concentration of the predators. And in space. So we'll need to change this to a partial derivative. Partial derivative dx by dt, dy by dt, and then we'll have a diffusion term, which I'll put for dx times grad squared of x, and diffusion dy, diffusion constant for the predators, grad squared y. So this is now a spatially explicit version of the Lotka-Volterra model. And the basic thing that we've done is made this a partial derivative, so it depends on time and space, and we've then added the diffusion term. And I've just said that it depends on here it depends on some diffusion constant that is characteristic of the prey, but in fact we could replace to make this more complicated but perhaps more realistic, replace this with a value that depends upon the concentration of the prey, because the more prey there are, then that will maybe make the rabbits more inclined to migrate away. So they will diffuse faster if there are lots of foxes around, for example. Anyway, so the point is that we can create, using this reaction diffusion idea, this spatially explicit version of Lotka-Volterra. And when we did the calculus part of the course and studied Lotka-Volterra, we said we're studying Lotka-Volterra not because we're interested in foxes and rabbits, but because this Lotka-Volterra type formalism has been used by people for theoretical history to model things like outbreaks of social unrest or the changing character of urban neighborhoods. So we may want to revisit those models and develop or use this reaction diffusion idea to make them have a more explicit spatial character to them.